Alrighty, maybe I will get started by just going over a few general things while folks continue to come on in to the room. So let's see, yeah, so the video is going to be recorded. So if you want to go back and take a look, you can do that at some point before the exam. Uh, let's see, what else I want to talk about sort of in general. So I don't have a great internet connection. In fact, I'm watching it kind of blink in and out in varying degrees now. So yeah, I don't have broadband internet. Isn't that kind of ironic? So if it glitches a little bit, let me know. Use the chat over on the right-hand side of the window there to ask me any questions. I'll keep an eye out on that chat room. So if you're wondering about something that I'm going over and you have a question about, just type a question in there and I'll try to answer it. And yeah, like I said, if there's a glitch or something due to some poor bandwidth going on, let me know too that if you miss something. No, I can't. Hopefully it will get better. Yeah, it probably doesn't affect the chat so much. But it certainly affects the video stream. So I imagine if you type in a question, I probably would see it more or less right away. It's the video streaming that's going to be glitchy. So I noticed that like in the recording, it's better. Like when I go back and watch the recording, it's not as bad. So that would help, I guess, if you wanted to go back and do that. Okay, so why don't we get started? This is the first exam. It starts on Monday, and you have until Wednesday night to finish it, Wednesday, 11:59 p.m. It's going to cover chapters 1 through 4. And of course, that starts with essentially an introduction to the course, what astrobiology is, what a habitable planet is, habitable world, life, kind of a basic general idea. What are the contexts that we're going to be studying life in the universe, right? We have planetary science, we have astronomy, and we have biology. Those are the three contexts we study to give us an idea for how life in the universe could be studied scientifically. And then we kind of move into the history of science, which is really a history of astronomy and history of how we knew about the universe. And then we kind of start in on the context. We start with astronomy. And then we go from there to learning all about galaxies and stars and planetary systems and things like that. And then finally, we wrap it up by chapter 4, which is all about planetary science. So let me get the book out, just so I sort of have it in front of me. All right. So that's the sort of general things we're going to be doing. So if you wanted to, addition to watching this, you could go over your quizzes. Those are a really big help in your homeworks. So if you really kind of go over those two things in addition to this study material, I think it will really help you with the exam. Okay. Here's the format. I think I've mentioned this before in one of our videos, or probably a couple of them by now. 40 multiple choice questions, 2 essay questions. You choose the 2 out of 4 to answer, so there'll be 4 different ones, but you only have to choose 2. The Mastering Astronomy assignments, as Joseph is asking. So yeah, that's what I mean by the homeworks. Those will really be what we're looking at here. And then, so it's going to be 90 minutes. There'll be a timer on it, and it will expire and then submit the test for you. So there's no outside notes or books or websites or communication with other people. So don't be opening browser tabs or anything like that. Is that a potato? It looks like a moon. I'm not sure what that is, Petey. um, so, so what is the weight? Derek had a question. What is the weight on essay questions and multiple choice? So the multiple choice will be worth 60% of your grade, and then the 2 essay questions will be worth 20% each. So that is the deal. So the essay questions, even though there's 2 of them, do count for a lot. So what I was about to say is, one strategy is to go to the essay questions first. They'll be at the end of the exam. So go to them first, and then choose which ones you want to do, perhaps. Read through them, see which ones you think you can answer the best. And then actually maybe just answer them. Just do them first, or at least create an outline of what you're going to do, what you're going to write. Or you can just do them. But then go back and do the multiple choice questions. That way, you don't get lost in multiple choice question land, because that's kind of easy to do, right? Kind of lose track of time going through all the different answer possibilities and things like that. So keep that in mind. You can do it any way you want, whichever way you feel more comfortable with. Hopefully that answers your question. So yeah, the essay questions are worth a lot. So spend a lot of time on them. There'll be instructions accompanying every essay question, so it'll be really clear what you're supposed to do, and 2 paragraphs will do it for that. It doesn't have to be long. You have to just make sure you get all the points across. That and usually the essay questions, just by nature, are going to require you to make several points or relay several different facts. Okay, so let's start with chapter 1, life in the universe. I apologize. It looks like the internet connection is worse than usual. So hopefully it's not glitching out too bad. If it's getting really bad, let me know. There's not much I can do, but maybe I'll kind of slow down a little bit and make sure you guys can get everything. All right. So the big thing is the universe is vast, right? The possibility of life beyond Earth is real. We are technologically advanced enough to begin to find life. And these are all reasons why life in the universe is really relevant now, as opposed to maybe even 20 years ago or even 10 years ago. In life, even simple single-celled life that has evolved independently from Earth is sure to be more fantastical than any movie or TV show you've ever seen. So one thing to keep in mind is that we've only found life in one place, and that is Earth. Earth is the only place where we have found life. So, it's easy to kind of get confused and think we have found life on Mars or Venus or somewhere else. We haven't. We don't know if life is anywhere. So that's why astrobiology is, a little bit of sort of guesswork a little bit. We don't know for sure if life can arise anywhere else, but there's no reason to think that the Earth is unique. The same materials exist all throughout the universe. Planets like the Earth, or even not like the Earth, have undergone very similar environments and other environments that could very well support life. And even though we don't know how life started, it went from chemicals to organisms that can replicate themselves and have other characteristics of life. We don't know that exact process. That's totally lost in the geological record. We have no idea. There's no reason to think that can't happen anywhere else. There's nothing special about the Earth in particular. I mean, it does have liquid water, but liquid water is plentiful throughout the solar system, as we'll find out. At least in relative sense. It's not hydrogen is the most abundant element, and so it readily makes water, and it's just going to the right place to find liquid water. But life could also exist with other liquids as well, as we're about to find out too. Okay, so our three contacts, we have astronomy. Our ancestors saw planets moving, lights in the sky. They named them after gods. We didn't know what they were. Um, and so when you look at the sky, it looks like everything is moving around us, right? If I look at the moon, it's going to move from one side of the sky to the other side of the sky during the night, and all the stars and the sun do that. And geez, why wouldn't we think we're the center of the universe if we saw that all the time? So this idea is called the geocentric universe, where the Earth is the center of the universe. And the universe, in ancient times was everything that we could see, right? Which is just like the stars and the planets, which are just lights in the sky, and the sun, and the moon. So that was the universe back then. We didn't know anything about galaxies or great attractors or expanding universe or the Big Bang or anything like that. The universe was 7 planets and the stars and everything you see around us on the Earth. Critical things about astronomy. The laws of physics have been observed to be the same throughout the universe. If life can evolve on Earth, it should be able to evolve on other planets as well. There are a lot of stars in the universe. This is sort of the point I was making earlier. There's a lot of planets like Earth or similar to Earth in that sense. And there are probably a lot of planets out there that are able to support life. So the universe is teeming with organic compounds on Earth, interstellar clouds, meteorites. There's just, we see organic compounds all over the place, literally inside meteorites that are falling to the Earth. Crack them open, oh look, organic compounds. But we can also see them remotely by looking at the light emanating from things like interstellar clouds. So we have organic molecules out there. Where would we expect liquid water to exist? Well, it can't exist like in the middle of open space, but liquid water could exist on planets and where their moons and the right distance from their star in what's called the habitable zone. The habitable zone is the distance from a star, and it's going to change depending on the star, what the distance is, but the distance from the star where if you put a planet that's like Earth, you could have a chance for life to possibly exist there. Doesn't mean there's life there. It doesn't mean that it's necessarily like Earth in particular, but it makes it more habitable. It's just the idea of having a habitable world. A habitable world is defined to be a world that has conditions suitable for life. Alrighty. So too far away from the habitable zone, the water will freeze, and that's not good for life. Really, you need liquid water, although that water could stay liquid underneath the surface or something like that. And then too close to the sun or to their star, and planets could have their water boil away and just exist as water vapor or just escape after some time out of the atmosphere and just not exist anymore. And we see that in Venus, where another process has taken hold where the surface is extremely hot, making it completely uninhabitable. Alrighty, so moving right along. So in 1995, or until 1995, we didn't have any evidence for any planets around sun-like stars outside of the solar system. So it's hard to imagine, right, that we didn't know that there used to be planets around other stars, but that was the common thing. We always suspected there were planets around other stars, but we don't know if it was common or rare. We kind of suspected it was common, but we just didn't have any evidence until we found the very first planet around a star in 1995, and it was totally what we did not expect to see. It was a Jupiter-sized planet orbiting a sun-like star, but much, much, much closer to even Mercury. So it was super hot, what they call hot Jupiters. So this is not what we expected. We expected to see something like our sun that has smaller planets closer in, maybe larger planets farther out. As you know, that the condensation during the formation of those solar systems sort of sets the composition and sets the sizes for those objects. And there's a reason that other star systems would be different than our sun and its planets. But that led us to an idea that, maybe Jupiters can form farther out, like maybe where our Jupiter is, and then migrate in to the to closer into the close to where it is now, like a very close orbit. Like for instance, some of these hot Jupiters orbit their planets, or orbit their stars, I should say, in a matter of hours or days. I mean, can you imagine that? So they're pretty close to their stars, and they're very hot, and they're all puffed up as a result, to varying degrees. So these are called extrasolar planets or exoplanets. And this just refers to any planets outside of our solar system orbiting other stars. Or not orbiting other stars, but just any planet outside of our solar system. Okay, the other context is biology. And so kind of similar to astronomy, and we assume that the same laws of physics exist throughout the universe as far as we've observed, and the same elements have been observed to exist in and around other stellar and planetary systems. It's reasonable to assume that the laws of chemistry, just like the laws of physics, I mean, there's, laws of chemistry are just extensions of the laws of physics, are also the same throughout the universe, right? And we know the molecules are out there. We see hydrogen and carbon and oxygen in the atmospheres of stars. We see, like I said, organic molecules out there in space. Everything looks the same as we see close to home, as far as the amount of different materials, like hydrogen being the most abundant element, helium being the second most abundant element. And then we see them obey the laws of chemistry too. So that's good, right? No unexpected surprises, at least as far as we can tell right now. We may need to venture out a little further to see if there are any exceptions or interesting things. It's called the anthropic principle, by the way, that everything is kind of uniform everywhere. Now, we don't know that to be true, but it's an assumption we have to make for all kinds of things like cosmology. The laws of physics are the same everywhere, but who knows? Maybe the laws aren't the same. The laws of physics aren't the same, like in other galaxies, for some reason. Maybe the early universe had different laws of physics. That's just purely conjecture. We have no real evidence for that, but it's something we're always kind of keeping in the back of our minds as we explore, especially like giant, cosmic distances and things like that. Not so much as things, around the local part of the galaxy. Okay, so we only have one example of biology, and that is Earth. We have organic carbon-based molecules, seem to be common throughout the universe, as we've talked about. And then laboratory experiments have indicated that the chemical building blocks of life can be combined to form complex organic molecules. And that's called the Miller-Urey experiment. Do you remember watching that cute little cartoon and the slides about the Miller-Urey experiment? And that's an important set of experiments, and people have kind of gone onwards and made various versions of that. But it doesn't create life. All it did was just created, or complex organic molecules out of some very basic molecules through different chemical processes that resemble the early Earth. Like, it was warm, they heat this goo up, and then you let it evaporate and then condense again and go through this cycle similar to maybe a cycle that happened on the early Earth. And it's warm, and then they hit it with electricity, I think, to kind of mimic lightning on the early Earth, to give it an extra spark, so to speak. But we didn't create life in these experiments. We've never done that. But it does show us that it's pretty easy to create complex organic molecules, at least. So that's a good step in the right direction. And then geology tells us that life arose very quickly after the Earth was formed. Like, as soon as Earth cooled down, as soon as literally, physically, those molecules could exist for some period of time, boom, life took hold. Again, we don't know exactly what happened when that took hold. Went from chemical to life, but it happened very quickly after the Earth, right after the Earth had the conditions allowed it to happen. So that tells us that life could arise on most habitable worlds, right? There's nothing special necessarily about the Earth that we know of in the context of the universe, but the fact that life on Earth seems to appear quite rapidly suggests that life could arise on most habitable worlds. And under a different range of conditions as well. Not just the exact conditions that we saw on early Earth, but on other conditions as well. So potential habitable places in our solar system include Mars, which had large oceans and flowing water billions of years ago. It has water ice today, just under the surface and above the surface. And we're seeing some evidence of liquid water coming to the surface and boiling away. And actually, we're not sure if that's liquid water or not. So that's kind of new information. It could be just carbon dioxide, but it could be liquid water as well, or maybe both. But we do have, some evidence for water underground, huge. In fact, my classmate in grad school just put out a paper last week or a couple weeks ago. Is all in the news that Mars has these huge underground ice deposits, these enormous ice sheets underground. So it's not inconceivable that there are pockets, maybe where there's some warmer pockets where that ice could melt and liquid water could exist. So life could possibly still exist underground where the conditions are much more favorable to life than maybe on the surface of Mars. Everything's still going okay with the stream. It looks to me like it's kind of going, maybe with the glitches and stuff. Hopefully the glitches aren't too bad. Alrighty, Europa, a moon of Jupiter. We'll learn all about this later. Under a thick ice shell, giant planetary liquid water ocean 60 miles deep. Europa has more liquid water on it than the Earth has. It's on a really deep ocean. In fact, it's so deep it can cause problems for life just because it's at the base of the ocean where we think life is most likely. It's a lot of pressure there, and there's no light throughout this entire ocean. It's complete darkness as far as sunlight goes. So there's challenges for life, but we see extremophiles on Earth survive in dark oceans just fine, right? Near hydrothermal vents, near the ocean floor. So who knows? It's hard to get to that water, but maybe we'll figure out a way to do that. And then also on the moons, Ganymede and Callisto, moons around Jupiter, also possible subsurface oceans there as well. Enceladus, which is a moon of Saturn. Enceladus is a moon of Saturn, ice-covered, kind of like Europa a little bit. Subsurface ocean thought to be a source of spewing ice jets from cracks in the southern polar region. Now, both Enceladus and Europa are spewing ice out into space, so they have liquid water forming somewhere underneath the ice or within the ice. I mean, in Europa's case, we know there's a pretty big ocean there, but Enceladus may have an ocean too, in contact with rock, we think, just because of the makeup of the water. We were able to sample it, luckily enough, due to having Cassini spacecraft orbiting around the planet Saturn. Is able to actually fly through this water and actually taste it. And it's salty and contain hydrogen compounds, which life could use for life. Energy, I should say. So it's very intriguing as far as the possibility for life on Enceladus goes. And then we have Titan, which is another moon of Saturn. A very unique moon. It's the only moon that has an appreciable atmosphere. It has an atmosphere thicker than on Earth's, and it's made out of the same most basic constituent, and that is nitrogen. But it's very, very cold there, and because it's so cold, like water would be as hard as granite. But it does have other liquids, liquid ethane and methane, like lakes of this liquid stuff on the surface, which is liquid at those temperatures and pressures, and lots of organic molecules. So, really intriguing place for astrobiology on Titan. Okay, so that's kind of overview of Chapter 1. Any questions about Chapter 1? Yeah, we also kind of want to emphasize that extraterrestrial life is defined to be any kind of life beyond Earth, not just in our solar system, but also anywhere beyond Earth. That's what extraterrestrial life is. Any questions about Chapter 1? Okay, so let's go to Chapter 2, the science of life and universe. There's a lot to cover here. Sorry the text is so small. Probably make your screen bigger to take a look at it. But you guys also have the slides too. So early civilizations know of and studied and utilized the regular motions of the sun, moon, and stars. The skies were our first clock. Way before we had any technology to make clocks, the sky, the motions of the stars, and the motion of the sun through the stars as the year went along, and the motions of the moon through the sky, for instance, as a month went along, were our clock. That's how we figured out what was going on, when it was time to plant crops, when it was time to harvest those crops, when it was going to get cold, all kinds of things. The sky told us everything. We have become completely disconnected from the sky just over the past 100 years or so, which is remarkable because that didn't used to be the case. All throughout human history, we've always had the sky there to help us. And just very, very recently, we don't even have any idea in our general lives what's going on in the sky. So it's really different. It's one of the really different things about human civilization right now. So Greek philosophers tested the ideas about what was going on. They had they had a very interesting culture of philosophy where they would try to come up with explanations for things. It was sort of the beginnings of science, as we learned, but it wasn't perfect. It wasn't, there were still people of their day. There were still gods, and there was still kind of an overarching, not dogma, but there were better philosophers who would sort of have better ideas, and they were better just because, well, they were more senior. This still kind of goes on today, right? It's not completely out of our society, but it played a little bit more of a role than the scientific method today would allow for. So, Anaxander proposed a geocentric model. This is way back, right, in like around 600 BC or so. So, wow, how long ago was that? A long time ago, a couple thousand plus years ago, 1,500, 1,600 years ago, 1,700 years ago. So he proposed geocentric model. Geocentric means Earth center, right? Earth is the center of the universe because that's kind of what it looks like. Totally understandable. He also suggested that life could exist in other Earths, maybe. Maybe there are other, planets out there like ours. So we created this thing called the celestial sphere, which is just like an imaginary sphere of where things appeared in the sky, because it looks like we're sitting at the center inside of a sphere, and everything's kind of rotating around us, right? And so the geocentric model, and so on that sphere would be the stars, and maybe on another sphere, or on the same sphere, depending on what model you're talking about, there would be the planets moving around, right? And the sun would be up there, all moving. They would be moving around the celestial sphere, around a stationary Earth. So it was pretty successful at explaining most astronomical phenomena, except for planets. Now, planets is actually comes from the Greek word for wanderer. And what planets do in the sky, as we found out, right, is from night to night. I'm not talking about during a night, because during the night, everything kind of rises in the east and sets in the west, right? Everything does that. But night to night, like if you would go to 8 o'clock and take a picture of a star in the sky, it would appear here. And then 8 o'clock, same time, the next night, the planet has moved against the stars. It's now over here. And next night, 8 o'clock, it's over here, it's over here, it's over here. So the planets are moving against the sky. So that's why they seem to, that's what they're called wanderers. They're wandering through the sky. So that was hard to explain with the geocentric model until Ptolemy came around, and he offered his own version of this. This is still in Greek society, and so he had an idea. So one of the problems is that the planets didn't just move around the sky from night to night. They actually reversed direction and then started back down again the same direction, kind of make a loop-de-loop. Again, as like a month would go on. And that loop-de-loop is called retrograde motion because it would go backwards as seen from Earth and then start to go forward again. So retrograde motion does exist. It is a real thing. It's the motion of the planets, or it's the position of the planets as observed from Earth. So Ptolemy had to figure out how to explain this retrograde motion with the geocentric model. Because if everything's going around the Earth in circles, nothing can change direction like that. So he came up with this crazy idea. That's not so crazy, because it did explain the observations. And that is a planet moved in these circles, within circles. So the retrograde motion will come about as the planet was going the opposite direction in its loop around the Earth, and circle around the Earth. Does that make sense? Hopefully that. Loops upon loops. So that's Ptolemy, geocentric. So we have the normal geocentric model, which is just the Earth at the center of the universe, right? The planet's going around. Then the Ptolemaic model, which is the planets going in circles within that circle, and that explains the retrograde motion that we see. Again, retrograde motion is real. We see it today. It's a fact, and as we find out, it's just a line of sight effect. And so here is the sort of the idea of the final geocentric model, right? We had where everything kind of are in these concentric, perfect spheres going around the Earth, and then in the Ptolemaic model, which is also geocentric, is kind of going in these loop-de-loops. These are called epicycles, these smaller circles. Okay, so that explained things well enough. And a lot of things started happening in Western Europe, of course, with the quote-unquote Dark Ages, which weren't really dark, but there was enough going on after the fall of the Roman Empire that it kept people occupied a little bit until, around the time of the Renaissance or so, when scientists could get back to this question. Things kind of progressed through the Dark Ages, just differently, in a different way. I mean, there was a lot of amazing art happening still. Music was pretty amazing. And there's all the other things too. But as far as this goes, things did kind of stay with the Ptolemaic model, and at least in Western civilization, that did not make a lot of progress. Now in the East, that's different. Muslim astronomers really did amazing work cataloging the stars. They named the stars. In fact, almost all the star names we have today come from Arabic names for the stars. And of course, we absorbed a lot of that in Western culture, of course, when the Muslims invaded during the Middle Ages. So, Western Europe, I mean. So, and then the Chinese as well. The Chinese did amazing work with astronomy too. So there was still work being done, but no huge breakthroughs as far as the models of the universe go. Until Copernicus. So there's a whole section in your book called The Copernican Revolution, and it didn't just involve Copernicus. This time period is just named after him because he kind of got the ball rolling with a really influential work. So the Copernican Revolution was Copernicus, of course, Nicholas Copernicus, but it was also Tycho Brahe, Kepler, Galileo, and Newton. These are all major players, ALL, sorry about the typo, major players in the revolution. So again, not just Copernicus, Brahe, and in that order, right? Those are the order that they lived and did all their important work. So let's talk about Copernicus a little bit. He was a Polish scholar. He was a theologian. He was a physician. And he lived from 1473 to 1543. Sorry, 1473, I think it's the number, right, to 1543. And so the work that kind of set all this in motion is his work, De Revolutionibus Orbium Celestrum, where we kind of abbreviate it by just calling it De Revolutionibus. I'm probably not pronouncing that Latin correctly. But on the day of his death, he's kind of struggled with this book because he was a very religious person. And so, of course, the topic of the book was maybe the Earth is not the center of the solar system. Maybe the sun is at the center of the solar system and Earth is just another planet. As you can imagine, the church didn't like that because all of a sudden it kind of challenged their authority under God, of course, where Earth was the center of the universe. Sounds crazy, but we're kind of going through the same thing right now. You can kind of figure that out culturally too. So maybe understand how ingrained some things can be and how difficult it is to kind of go against that, or how how science and independent thinking can threaten religious authority. So anyway, he didn't publish it really until he was on his deathbed, and the idea revived Aristarchus's radical idea from 1800 years ago that there was a sun-centered solar system. So this was not a new idea. But Aristarchus' idea back in ancient Greece didn't last very long. It's possible that people accepted that for like 100 years or 200 years or so, that the sun was the center of the solar system. But then it kind of got bowled over by the Ptolemaic model eventually, which seemed to describe things a lot better. So, and we weren't sure if, Copernicus knew about Aristarchus' idea. I mean, it's not like he had Wikipedia right there to look it up. But he did refer to it in his works that he knew that existed, at least after the fact. So no, we don't know if he just took his inspiration from that to begin with, or if later on he kind of figured out, hey, this is kind of an idea that also someone else had too. Anyway, he found simple geometric patterns linking the distances and orbital periods of the planets. So kind of like Kepler's third law, but just done very basically with circles, right? All the planets went around the sun in circles. So the good thing is that much simpler than the crazy geocentric circles within circles idea of the Ptolemaic model. The bad thing is that it did not do any better at predicting the position of the planets in our sky. That sounds crazy, right? How could that be? Sorry about the buffering. Hopefully that will be better. Again, like I said, the recording is going to be better. So if you want to go back and maybe take a note about what part you want to take a look at, the recording, I bet will be better when you go back and look at it. But again, if you have any questions about the buffering, let me know. Hopefully it's not too bad. Okay, so sorry, where was I? So yeah, it didn't make any better predictions. That's a big deal, right? It wasn't any reason to think it was going to be, you think it would be better, right? With the sun at the center, shouldn't everything kind of work out? So there's something Copernicus was missing, and it was kind of fundamental. But he didn't know what it was. I mean, he died really before it was published or as it was being published. So he really didn't live to live in the aftermath. And it didn't take hold. I mean, it didn't really cause a huge stir at the beginning, but it's caused some people, sort of inspired people to take up this cause of the heliocentric universe. Again, heliocentric, meaning sun-centered. Okay, Tycho Brahe. He was an eccentric Danish nobleman is a mathematician. He was famous for having a gold nose. You'll hear this a lot. He lost it in a sword fight at 20 with another student over whom was a better mathematician. At least that's how the story goes. And he read The Revolution of Us, and he really appreciated how simple it was. So Brahe had an even bigger problem that he had an observatory, and he was really the premier astronomer at the time. He made some very precise measurements about the positions of the stars in the sky, and also the positions of the planets against the stars in the sky. So when he started applying, Copernicus's ideas, he couldn't make it work with his observations. It did not fit his observations. So he tried to make all these crazy models, like, well, maybe the sun is at the center, and maybe Earth and Venus like orbited the sun together, or something like that. Maybe his other objects orbited other objects. Maybe that would explain some of this retrograde motion problems he was trying to figure out. Again, the real problem was retrograde motion, especially with Mars. But he couldn't figure it out. So he actually hired someone named Johannes Kepler, who, again, a lot of these guys who are mathematicians, who are very learned noblemen, are also very deeply religious, or clergymen. And Kepler was no exception. So he was hired by by Brahe to kind of come up with a solution. But Brahe was worried that he would not get credit, that Kepler was going to do this amazing discovery. So he kept, strangely enough, all the good data for himself. He would not let Kepler at, for instance, all the positions of Mars that he had taken that Kepler really wanted. Kepler became very frustrated and actually left the observatory that Tycho built, and then with his family, and then he kind of went somewhere else to work for him. And so, he sort of kind of kept in contact, and he sort of still stayed employed and associated with Brahe until Brahe died. And then after Brahe died, ta-da, all his data was available to Kepler. And sure enough, I guess Tycho was right to be worried, if that was his worry, that Kepler would be successful, because that's what he needed. That planetary data is what Kepler needed to complete figuring out what was going on. So the problem was, why everything wasn't working, was that everyone was using circles. The planets were going around the sun, including the Earth, was going around the sun in circles, and that is not the case. So once you started using ellipses, then it started working. So ellipses are another conical section, right? If you take a cone, and then you start slicing the cone in different areas. So if you take a nice parallel slice of a cone, that's a circle. But if you then take like an angled slice of a cone, then that's going to be an ellipse. And then you take a really angled slice of a cone, and you go at the bottom, then that's going to be a parabola. So it's these conical sections that was sort of going to work. So he made his 3 laws of planetary motion. The first law is that the orbit of each planet about the sun is an ellipse with the sun at one focus. So an ellipse has a couple different things to look at. It does have a center, but it also has these foci. And there's 2 of them on either side. So here's a beautiful oval shape, right? There is a center here, but there's nothing really there particularly. Well, it's really interesting here is you want the focus. So the sun is at one focus of this ellipse with nothing at the other end of this focus. And the semi-major axis, which is often abbreviated as A, that is this distance here, which is the average distance of this planet going around the orbit from the star. It doesn't look like doesn't look like that, right? If I took the average distance this planet was away from its sun as it goes around in this blue orbit, it didn't seem like it would come out to be this distance, but you can actually prove that mathematically. So it's not something that's obvious. Don't worry if that's something you never got. But yeah, that's the average distance away from the sun, this semi-major axis. It's just one property of the ellipse. Perihelion is the closest point to the sun, so right here. And the aphelion is all the way over here. And it's the farthest point from the sun in the orbit. Okay, Kepler's second law. A planet moves faster when going around the sun as it gets nearer and slower as it gets farther away. Sorry, I'm using my cursor. You guys can't see my cursor. Apologies for that. So, near perihelion, it's moving fastest, right? And aphelion, it's moving slowest. So this can get confusing with the third law, talking about orbital speed. But this law just talks about the one orbit. Like how fast does the planet go in its orbit around the sun? So it gets faster as it gets closer, farther away it gets slower, and it's sweeping out equal areas in equal times. So if you had a stopwatch and you were timing it as the planet went around, as you saw in that interactive that we messed with, it would sweep out equal areas at equal times. So this area, for instance, is equal to this area, as long as they're both same amount of time has passed. Okay, now Kepler's third law has to deal with all of the orbits of all the planets. So the idea is that they all obey this precise mathematical relationship, and that is p squared equals a cubed, or a cubed equals p squared. So it's a semi-major axis cubed is equal to the period squared. So if you know how long it takes for a planet to go around the sun, and we can do that pretty easily, right? We can just measure how long it takes, like Saturn, for instance, to go through the stars all the way around. Turns out it's about 30 years. Or Jupiter or any other planet, to see how long it takes to go around in our sky once against the stars. And then you could figure out how far away that planet is away from the sun. That's amazing. I mean, all of a sudden we're able to do that just by looking at like these conical shapes. And that's because we were able to study like the retrograde motion of Mars, like thanks to Tycho Brahe. So that's an amazing leap, right? So remember that p squared equals a cubed for the third law. Semi-major axis is in astronomical units, which is just the average distance from Earth to the sun, and p is the period of the planet in Earth years. You can measure this in other units too, but then you need like a constant of proportionality here, then it's just proportional. If that makes any sense to you guys. So p squared equals a cubed. Okay, so then along came Galileo. He was probably the first real scientist, really. He did some amazing work when it came to figuring out a lot of different things about astronomy and gravity. So he went on to argue all the old arguments against a heliocentric theory. Now, back in the day, in ancient Greece, when there was an idea that the sun may have been at the center of the universe and the Earth went around, there were all these really good objections. Like, why doesn't things fly off the Earth if we're traveling so fast? Why do birds fly through the sky? As soon as they leave the branch, shouldn't they just like be flying away? And things like that. So Galileo answered these questions. And then he did a lot more work. So he heard about this thing called a telescope, and then he built one of his own just by hearing about it. Could have put a couple lenses together in a tube and sort of perfected the idea after a couple tries and started to look at the stars with it. He was the first person to write down what he saw after looking at things in the sky with a telescope. So it's a big deal. And so he started making sketches. So he saw sunspots on the sun, like little blotches, the hills and valleys on the moon. Suddenly the moon wasn't perfect anymore when the sun wasn't perfect anymore. And then he saw a comet, and then the appearance of a supernova. He was lucky enough to be around when a star exploded, so he actually saw that. that the heavens were changing, and they weren't like immutable and impermanent. They weren't the realm of the gods. There seemed to be all kinds of interesting, weird, imperfect things up there. And then he also observed Venus. This was a real big piece of evidence for the heliocentric model. So in your slides here, you can kind of see the left part of this diagram here, which is the geocentric view of the universe. And there is Venus going along on its epicycle, and the sun is out there and going around the Earth. So you would see the phases of Venus as the sun was lighting up Venus in that way. But on the right side is really what's going on, of course, with the sun and Venus. You would expect to see the phases of Venus this way, with different sides being lit up by the sun. We saw, or Galileo saw, the ones on the right. And that gave him a huge amount of evidence that, wow, we are probably not in a geocentric universe. And then along came Isaac Newton. And Isaac Newton came along and he kind of put everything together, right? He had this amazing scientific treatise called the Principia. And the Principia sort of gave birth to modern physics. It also invented a new branch of mathematics called calculus. So he co-invented calculus. And he invented physics at the same time. He also came up with laws of optics separately than this. So it's a pretty amazing guy. And he derived Kepler's laws from this new mathematics. So he was able actually to prove mathematically everything that was going on. So he proved that, sure enough, that the Earth did go around the sun. The moon went around the Earth, though. And Kepler's laws were true, and he could prove that mathematically and actually expounded on it. And he said that the same forces, he invented this thing called a force, due to gravity, due to the attraction of different objects with different masses, that was governing the motion of the planets. And it's the same force that governs all the motions that we see here on Earth. And suddenly, the heavens broke apart religiously. All of a sudden, the heavens were not the realm of the gods or God. They were just another place where the laws of physics, where the same laws on Earth, governed in the same place up there. So that was a pretty existential result. Just trying to figure out why Mars goes backwards in our sky. That's pretty amazing. So how did it change the debates on extraterrestrial life? Well, among many different ways, it set the stage for an entire revolution in astronomical discovery, in philosophy. So as soon as we figured out that the planets weren't perfect realms or spheres unto themselves, we started imagining life there, right? As soon as we saw mountains on the moon, it's like we could imagine like there's like crazy bats that flew out of those mountains, right? Because of the low gravity. And we could think of like Venus being a hot tropical area because it was closer to the sun, so it had to be hotter, right? So there had to be jungles there, and there had to be life there. And so we saw life everywhere as soon as the planets became worlds. So what is the scientific method? What did this give birth to? What did we inherit from all this that essentially governs our entire society today? Well, first we make an observation. We have a hypothesis. We ask a question. It's sort of the hypothesis will help to answer. And then we make a prediction of an experiment or an observation. And then we look at the results of that experiment or the observation and see if it supports it, see if it's supported, if it ends up being, the hypothesis ends up being true. And if it doesn't, then we have to go back and maybe suggest another hypothesis and repeat this process again. If it is true, then we go back and maybe make an additional prediction and test that as well, or make that hypothesis broader, try to test out to see how valid that hypothesis is. So a hypothesis is an educated guess. The big thing I wanted to get across to you guys is what a theory is, right? A scientific theory is the result of all that. Even though it's named theory, it's not just an idea you have. A theory is like a law. It's like a physical law. It's survived a lot of scientific rigor. So like the theory of gravity or the theory of relativity, right? Those are all like basic tenets, like foundations of science you could, really rely on. So that's what a theory is. So you may have a theory, but the theory of gravity is well tested, and you can probably count on it being true. So there are a couple of things about theories, though, you should know, even though they're like held up high, right, as almost laws of science. So a theory shouldn't need modification, really, to come up. If you come up with a theory, it shouldn't really need modified for different applications. It should be kind of an overarching general theory. A theory should have a powerful ability to predict and explain observations. Kind of makes sense, right? It should predict pretty well what's going on. But a theory, this is kind of like a fail-safe, right? A theory should also be unprovable. In other words, you can never put a theory in such a place where it can't be proved wrong. You can always prove wrong. It's something wrong in science, right? If you have the evidence, everything is vulnerable in science. But, sometimes you need a lot more evidence, and you need a lot more scientific rigor to prove a theory is wrong. Oftentimes, it's usually find an exception to the theory that, suddenly that theory is not so broad anymore, but it's more limited, and then maybe an overarching theory a new theory is going to take its place. So it's unprovable. You cannot really prove a theory beyond all doubt. You can always falsify a theory. It can always be proved wrong. And that's the important thing about theory, about science. Okay, life in the universe, stars, galaxies, and the universe. All right, so let's talk about the first thing, a light year. What is a light year? Is it a unit of time? No. Is it a unit of time with less calories? No. It is a unit of distance. A light year is like a meter. It's like a foot. It's like an inch. It's just another way to measure distances. It's just the distance light travels in a year. Wish they would have named it something different just to avoid the confusion with time, but it's not a unit of time, it is a unit of distance. So it's really big. It's about 10 trillion kilometers. Light does travel fast, so in a year, if you measure how far it travels, it's pretty far. So we're talking about a pretty big unit of measurement, but the universe is way bigger than just a light year. For instance, the nearest known star to us Proxima Centauri, which, by the way, has a planet in the habitable zone, which we'll talk about later, is about a little over 4 light years away. So if light left Proxima Centauri, it would take over 4 years for it to get to Earth. So that's how it's related to time. And we're talking about the light traveling. But it's a unit, light year is a unit of distance. So when we're talking about galaxies, though, we talk about millions of light years. So the universe is enormous. Mega light years, right? 1 million light years. Or giga light years. 1 billion light years. Or 10 to the 9th light years. Okay, so there's a really important context that the universe gives us for life. And they all point to there being perhaps plentiful life in the universe. So the universe is vast and old. It is huge. I think the universe is infinite in size. It's 46 gigalight years observed. I think I mentioned this in the slides, that this radius of the universe, observable universe size, is different than the one in your book. So know the one in the slides. Don't worry about the one in the book. It's just defining observable universe a little differently than most astronomers do. So yes, the size of the observable universe is known to be about 46 gigalight years. It's not 13.8 gigalight years as in the book, the way we're going to define it. So keep that in mind. Good reason that you're watching this video. So anyway, it's incredibly old though, 13.8, almost 14 giga years old, so billion years old, almost 14 billion years old. This implies that there are an enormous number of planets and moons and enough time for life to begin and evolve in great numbers. The universe is huge. It's filled with so many stars, it's hard to even really comprehend. And even more planets that we can't even comprehend. So life could be very well plentiful. Another reason for that is that the building blocks of life are all widespread. We kind of talked about that. We see organic molecules, we see carbon and oxygen, nitrogen, all the building blocks we have here on Earth. We see them spread throughout the universe, both in other solar systems as far as like disks around other stars, but also in meteorites, in stellar atmospheres, and nebulae. They're just everywhere. Everything seems to agree that there's nothing special about the Earth chemically. So that gives us a lot of hope. And of course, the anthropic principle, the same physical laws that operate on Earth operate throughout the universe. So that is that everything is pretty consistent. We haven't observed anything that would cause us to believe otherwise, but so we're going on that assumption. It seems like chemistry works everywhere the same way, at least we've seen so far. So here's the size difference, right? We have, you should definitely know this for the exam. We have the Earth, it's pretty tiny, right? It's 10 to the 4 kilometers. That's a fraction of a light second. Again, light second is like a light year, but it's a tiny distance, small distance. And then we have the solar system, right? Many light hours. So it takes light hours for it to get out here. So it's many light hours in radius. Then we have the Milky Way galaxy, which is, of course, contains hundreds of billions of solar systems, stars. So that can be 100,000 light years or more across the Milky Way galaxy. That's our galaxy. The Milky Way galaxy is not the solar system. That is not the name of the solar system. The Milky Way galaxy is all the stars, including our sun, like a giant city of stars. Okay, so that's our galaxy. Again, our galaxy is not the solar system. This is just tiny. This is one star, our solar system. This is 100 or 200 billion stars in the Milky Way galaxy. But out of that galaxy, there's even more galaxies all over the place. And so the local group is a kind of a local neighborhood of galaxies. This goes out to about 6.5 megalight years or so. To our kind of local group of galaxies, which includes the Andromeda galaxy. And then even bigger than that is the local supercluster, which is about 100 million light years, an enormous amount here of galaxies, so even more galaxies. So know this kind of progression from small to enormous, right? Local supercluster. It gets even bigger than that too, but kind of know this scale. Okay, and that's kind of what I was talking about. This is kind of like the law, kind of written out here, right from Earth, the smallest, the solar system, all the way out to the supercluster, all the way out to the universe. Okay, the universe is made of mostly stuff we have no idea what it is. That's true. This is a new revelation that just came into astronomy about 25 years ago or so. Maybe, well, I guess it's been 20 years now. 21 years, 22 years. So we like to say that the universe is made of mostly hydrogen gas, right? Mostly stuff we can see. But that's actually not the case. As it turns out, the stuff we can see and the stuff we are used to seeing around us, hydrogen, helium. Well, hydrogen is the most plentiful element. It doesn't make up most of the universe. Most of the universe is the stuff we can't figure out that's making the universe not just expand, but contract. It's like an energy latent in the fabric of the universe itself. So this is called dark energy because we have no idea what it is. It's dark. It is in the form of energy, and whatever it is, it's causing the universe to accelerate. So we talked about the Big Bang, right? And expanding the universe. We think of it like that. But it's actually not the case. What's actually happening is that the universe is accelerating. So it's expanding and it's getting faster as time goes on. Something is causing that. So you can have a Big Bang and things can be expanding and not need any more energy than you had in the Big Bang to make it expand at a constant rate. But if you're accelerating something, you need energy to do that. And there's something about the universe that contains this mystery energy that's causing it to accelerate. We have absolutely no idea what it is. We're just beginning to wrap our heads around just different ideas of what that form would take. So most of the universe is dark energy. What about the other part of it? Surely that's the stuff we know, right? No. This is also stuff we've just discovered in the past 30 years or so. We have no idea what it is. It's matter, but it's kind of a weird amount of matter. Sorry. What is the next slide there? Okay. So it's matter, but it doesn't seem to emit any light. It doesn't seem to reflect any light, but it does seem to gravitationally interact with the matter we know and love. So we call it dark because it's just unseen. We have no idea it was there until we really looked at gravitational effects of regular matter and figured out that, wait a minute, there should be a lot more stuff there if, like, for instance, galaxies are going to stay together and not fly apart. There needs to be something holding that together. Now, we can't really account for any more material that we can see. Like, there's not extra stars in there to provide all that much extra matter that would hold the galaxy together gravitationally. But there's some massive amount of unseen material, completely invisible at all wavelengths, that light seems to travel through, but still has a gravitational effect. Again, we have no idea what this is. Again, we have absolutely no clue. We are just at the very beginnings of understanding this. So that makes about 27% of the universe. So dark energy, 68% of the whole universe. Matter and energy are interchangeable, right? As we found out. So when we talk about how much the universe is made out of or what it's made out of, we're really talking about the energy as well. So dark energy, 68%, dark matter, 27%. And then ordinary matter is just a measly 5%. And that's all the hydrogen and helium and everything that you and I are made out of. Again, mostly hydrogen we're talking about. Makes up most of this ordinary matter. But a little tiny sliver is carbon and oxygen and other stuff too. Which is tiny, tiny percent of what the universe is made out of. So interesting, huh? Okay, so brief history of the Big Bang. As I mentioned, the Big Bang happened. We don't know what caused it, but all the space, all the time, yes, even time, and all the energy of the universe was in a singularity, in a tiny little infinitesimally tiny spot. What was on the outside of it? We don't know. We don't know what's outside of the universe, but it's whatever the universe is in. It started off as a tiny point. It expanded out. It wasn't an explosion. It's just an expansion. You'll see like huge explosion sounds, and right, it's like you'll see like these animations on like the Discovery Channel. It's like, and it's like your hair blows back, and that's the Big Bang. It's not that at all. It's just a nice expansion, very fast expansion of unimaginably dense amount of energy and time and space all in one spot. So outside of that, we have no idea what's outside of the universe. That's how the universe started, and then it's accelerated, right? Then it really accelerated to something called inflation. It got really big, really fast, very quickly after it formed, after the universe started expanding. And then it's been expanding and accelerating ever since. So we have no idea about that inflation either. It does seem to solve a lot of problems. It does seem to be the current model that people are going with, this sort of sudden inflation in size. So that's the Big Bang in a nutshell. So we know this. We know the universe is expanding. Why? Does it seem like a good idea? No. We can actually observe it. If we observe galaxies all around us that are, millions of light years away, everything seems to be moving away from us. Everything. I mean, maybe a galaxy here is like gravitationally coming toward us, through local gravitational effects. Other than that, everything in the outer part of the universe is moving away from us. So we're the center of the universe, right? No, we're not. So as it turns out, if you're on a surface that's expanding, like if you have a balloon and you're blowing it up, and that surface is getting bigger, every spot in that balloon, if you're observing from that spot, would appear that everything is moving away from it. Kind of makes sense, right? Because the balloon itself is getting bigger. That's what's happening. The universe is expanding. Space is expanding. So when we see these galaxies have a red shift, a shift toward the red end of the spectrum, which tells us their Doppler shift is moving away from us, that's what's going on. The universe is expanding. And it actually, if we look farther away to dimmer galaxies, they're moving even faster away from us. This is exactly what you would expect to see for like a three-dimensional expanding object. Those things that are farther away from you are going to be looking like they're, because they are, moving away from you much, much faster than the things that are closer to you. Pretty wild. So we run the clock backwards, all the way back to that singularity point. That's where we get 13.8 billion years. And that's a pretty amazing accomplishment. We figured out how old the universe is to within a pretty good agreement. We've also did this through the cosmic microwave background radiation as well. That provided a really nice constraint on that number. Okay, so let's go over stuff. What does stuff mean? Stuff is like the stuff we're used to, like hydrogen, helium, the periodic chart. What does all this mean? So an element's atomic number is a number of protons in the nucleus. So hydrogen has 1 proton in the nucleus. Atomic number is 1. Helium has 2 protons. That's why it's helium, because it has 2 protons. The protons define the element. So it has 2 atomic number. Lithium 3, carbon 6, and so on. Now the atomic mass number is the number of protons and neutrons in the nucleus. So not just protons are in the nucleus, but neutrons as well. The number of neutrons does not change the element, but that does give another isotope of the element that you're looking at. So you can have a different number of, for instance, you can have, instead of 2 neutrons, like in helium, you can have 3 neutrons in the helium nucleus. So that would be an isotope of helium. But you don't change elements until you put more protons in there. Now, what do the isotopes, how does that affect things? A lot, actually. You can change the entire chemistry of the element by that. And the element can be unstable. Like certain isotopes just can't hold that many neutrons or that few neutrons in the element, and it will break apart. So that can have effects too. That's radioactivity. That's what we're talking about when we're talking about things being radioactive. So all known elements, including 94 naturally occurring elements, plus 24 man-made elements that we make in a laboratory, like plutonium, and other elements, equals 118 currently known elements. Okay, so we have 2 different kinds of planets in our solar system. We have terrestrial planets, right, the inner planets, and we have Jovian planets. They have some very enormous differences. First of all, their distances, right? Terrestrial planets are small, they're rocky, and they're close to the sun. We have, they all are, right? We have Mercury, Venus, Earth, Mars, Those are all planets that are, relatively close to the sun. We have no gas giants. We have no Jovian planets that are close to the sun like that. Some solar systems do, but we have a beautiful solar system that's more or less held its positions, or planets were more or less held their positions at formation to within a certain amount. So then outward, the planets are really different. They're not rocky. The planets are gaseous and enormous, mostly made up of hydrogen with some helium, and the composition is very much like the sun. And that's Jupiter, Saturn, Uranus, and Neptune. So those planets are less dense than the terrestrial planets, Jovian planets. So Jovian planets are less dense, they're larger, they're more massive. So they are more massive, but they're less dense. Does that make sense? Saturn has like an overall density that's less than water. You could float Saturn in a giant bathtub if it was big enough. That would be something, by the way. So they're really different. And the outer planets have rings, the Jovian planets. The terrestrial planets do not have rings. The terrestrial planets have very high densities, made of heavy elements like silicon and magnesium, iron, of course, which are heavy elements, heavy occurring elements, but mostly silicon and magnesium, oxygen, heavier than hydrogen and helium for the terrestrial planets. And few or no moons for the terrestrial planets. Out on the Jovian planets, tons of moons. 60, 70 moons each for Saturn and Jupiter. Okay, so how did all this come to be? We can come up with a theory, believe it or not, that can explain all of that and the motions of it all. So here are the different formation ideas, or formation steps, I should say, of the solar system. We start off with an enormous cloud of gas and dust. Mostly gas, almost all gas. And it's just floating out there in space. It's nice and cold. And it could be, this cloud of gas could be tens of light years large. It could be enormous. And then parts of it are going to start to contract. Just literally something's going to disturb it, and the gas molecules are going to start coming together just from their own gravity. And as they do, they're going to get hotter and more dense, right, at different parts. So this cloud, this enormous cloud, is actually going to give birth to several stars. And we think our sun was born with several other stars. Where are our solar brothers and sisters? They're lost to history, unfortunately. Stars throughout the galaxy do dissipate over millions and billions of years, so they're around somewhere. We just don't know where they are. Or if they're even stars that are nearby us right now. We just can't, there's no way to tell. But they're probably scattered throughout the whole galaxy as we've been orbiting the galaxy. Anyway, so let's concentrate on one of those little areas that's getting denser. So it's getting denser and denser and denser, and as the cloud collapses, it starts to spin, and it's from a conservation of angular momentum, and as it spins, the whole thing starts to flatten out like a pancake. That's again also from angular momentum. It's just kind of how things work. And at the center, it's going to get really hot here. Everything is kind of swirling around in the same direction. You'll end up with this giant cosmic pancake. It's kind of cosmic record, I guess, right? Cosmic vinyl that's spinning around the central core. So the central core is getting hotter and hotter. It's hot there, right? All these gases are bumping into each other. The temperature is high. The closer in you get to the center. It's colder around here. So all this gas, it's still gas, remember, it's going to start to do something. It's going to start to condense into blobs. How does it do that, or why does it do that? Well, how it condenses into blobs depending on how hot it is. So here in the, I should say here closer to the center, the temperature is warm, right? And the only thing that can condense into blobs are like elements like magnesium and oxygen and silicon, and things that make rock. It's hard to think of rock as being a gas, but it is. It can be a gas at really low temperatures and pressures. And that's what the nebula, the gas, was made out of before it condensed, or before it collapsed and started condensing. So rock condensed out of gas here because it was too hot for some of the other elements to condense. And we'll talk about that in a second. So I keep using my cursor, so apologies for that. It's a bad habit. You guys can't see my cursor. So out here in the outer part of the solar system, it's much colder, right? Out there, you have the ability to condense ice. Literally like all kinds of different ices. Water ice, so hydrogen starts to combine with oxygen. It can combine with carbon. It can combine with nitrogen. Here, closer to the center, it's too hot for that, right? You can't have ice in an oven, right? What's going to happen? It's going to turn to liquid or it's going to evaporate, right? In the case of this, it would evaporate. So you have to go way out there to get ice. So that's a critical difference. That is the main difference why we have terrestrial planets and Jovian planets. And we'll talk about that in the next slide. So things start to clump together, right? The stuff that clumps together closer in here are all the rocky bits. So they form rocks. However, there's not much rocky stuff. Most of the nebula, most of this gas that we started off with is hydrogen and helium. So that's still gas just hanging around. All the rocky bits, it doesn't make a whole lot of material compared to the amount of material available. So that's why the terrestrial planets are pretty small. There's just not a lot of material there that's rock. Out here, though, the stuff that you can accrete on the planets is ice that contains hydrogen. So hydrogen is the most abundant element in all this stuff. So there's lots of it. And all of a sudden, you're able to accumulate a pretty big planetary core that has enough gravity to keep in the rest of the gas that hasn't condensed into ice. And so it not only gets bigger because it's the ice out there, right? The ice creates a big core, but then it's big enough gravitationally to hold on to any gas it encounters, any hydrogen gas it encounters. Here in the inner part of the solar system, we have our small rocky planets. They don't have the gravity to hold on to the gaseous hydrogen that's in there. So the big takeaway is, why is there a difference in why did Jovian and terrestrial planets end up so differently? Temperature. It is the temperature of this solar nebula that defined how big things got because of, previous slide, condensation. Okay, so we got things creating big giant blobs. We have the larger blobs out here that are hold on to hydrogen. That's why they have big giant atmospheres, because it retains all the gas, become very large. Here we have tiny terrestrial planets in comparison. And then finally, we forgot about the center here. It gets so hot and so dense that nuclear fusion starts to occur and the sun turns on. And all this energy comes out, right? And the energy, all these particles these charged particles start coming out, the solar wind, and the charged particles hook up with the remaining gas that's in the solar system, and it clears the gas out. And it blows the dust out too. So that's when the composition of the planets are solidified. Because when the sun turns on, it clears out, blows out the remaining gas and dust, and then the planetary composition is locked in. That's the clearing stage. And that's all you need to know about how we came to be. Any questions or anything? You guys still with me? I've been keeping my eye on the chat. We'll try to finish up here pretty soon. We're in our last chapter. All right. Let's talk about rocks. All that rocky stuff. We're going to concentrate on the Earth. But the Earth's geology is a great stepping stone to understanding the geology of other planets as well. Okay, so the geologic record tracks the evolution of the Earth as evidenced by the rocks, fossils, and other debris. It's left over from the gradual physical changes. So we have three different kinds of rocks, and they represent how the rocks have changed over time. And you can change one rock type into another. So if you have igneous rock, that's made from molten rock that cools and solidifies. You have metamorphic rock, which has been structurally or chemically transformed by high pressure or heat, but that didn't melt. So you can take rock and like gets crushed by, it goes underground, like deep underground, where it's high pressure and temperature, and it just changes it, but it doesn't melt it. It doesn't completely melt it. But then you have sedimentary rock too, which is rock by, like you can have like at the bottom of like a river delta, or maybe in a lake where a stream comes in and deposits silt, and that silt will go to the bottom of the lake and start forming layers and layers and layers and layers, and that will actually form a rock. So that's the gradual compression of sediments such as sand, silt at the bottom of seas and swamps. So we see that a lot. So you can go from one rock type to another. You can go from igneous rock. So first of all, you get metamorphic rock, and if you have more pressure and temperature, you could melt it, right? It's become igneous rock. That's molten rock. But then say you took that igneous rock, that molten rock, and it found its way into a stream, and then of course cooled off, and then ended up as a sedimentary rock at some point, right? Under a lake bed or under an ocean floor. But then say that ocean floor is moved by plate tectonics in a subduction zone, and it gets jammed under intense pressure and heat, but it doesn't melt. That sedimentary rock can become metamorphic rock, and so on in the rock cycle. Okay, let's talk about the age of the Earth. The oldest known evidence in geologic record is that the Earth the geologic record is about 4 billion years old. That doesn't necessarily mean that the Earth is 4 billion years. We need to look at different lines of evidence because there's things that could affect how long of the geologic record we could go back to. So zircons, or zirconium silicate crystals formed in the early solar system, they place the date of the Earth about 4.4 billion years ago. Samples of lunar regolith that we got from the Apollo missions, that dates the Earth to about 4.4 billion years ago, because we do think the moon did form with the Earth. So they're the same age. So samples of meteorites that fall here on Earth place the age of the solar system at roughly 4.6 billion years. So that's the solar system. So meteorites, have their own thing going on. So it seems like they formed about 4.6 billion years ago. So that may be like when things started to condense, perhaps out of the solar nebula. So if we kind of look at these in different ways, we come up with an age of the Earth, finally, that's about 4.5 billion years old. That is really old. Think about how old that is. How many eons, how many centuries, how many millions of centuries that is. It's tremendous. Okay, so let's talk about cratering in life. We observe craters in the moon as well as on Earth. Craters can not only indicate the size of the object that smashed into the Earth, and we bring this up because Earth's early history is all about cratering. There were things crashing into the Earth constantly, very early on in Earth's life. In fact, that's how we think the moon was created, right? A Mars-sized object smashed into the Earth, I should say, and then just kind of broke off a huge chunk of the Earth, combined with that other object to hit us, and reformed the Earth and the moon out of the same mess. So that's why the moon is almost like our sister, right? Earth's geologic processes, though, resurface the crust, constantly changing the crust via erosion, volcanism, earthquakes, plate tectonics, and more, steadily erasing evidence of craters. But we still see evidence of craters. Sometimes it's just harder to see. It depends on how old the crater is and where it is. For instance, we saw the crater that probably was associated with the asteroid that hit the Earth that killed off the dinosaurs, for instance. But that's hidden under, the water and under the ocean, essentially, off the Yucatan Peninsula. It was really hard to see until we had the technology to do that. And that's only 65 million years old, which is pretty recent history compared to everything else on the Earth. We have to look at the moon. The moon doesn't have an atmosphere. The moon doesn't have water or volcanism anymore, or plate tectonics. It is literally like a time machine. It is like a time capsule, I guess I wanted to say, a time capsule, in preserving what happened right after things were formed in the solar system. At least as far as Earth goes. We can look at other planets too and look at cratering and figure out the same thing. So we know that there's this thing called this heavy bombardment period, which is a 750 million year stretch where things were just constantly being bombarded and the Earth's surface was molten. So yeah, for like a million years, for almost a billion years, I wanted to say, that the Earth had a really bad time. It was being hit by all kinds of things that included the thing that created the moon. And then there's this thing called the late heavy bombardment, which happened after the heavy bombardment. The bombardment shouldn't have been over, but all of a sudden we seem to have gotten hit again by a whole bunch of meteorites, meteoroids. And that may have been due to something happening in the solar system. Maybe Jupiter started migrating in, just from orbital dynamics. Could be moved closer to the sun over time, and that could cause a huge gravitational disturbance to where there was maybe some stably orbiting asteroids, and that caused us to get hit by a bunch of asteroids again. Okay, so the whole of the geologic record is taken into account. That's when we talk about the Earth's history. We break it down into eons, eras, and periods. We don't go into really a lot of detail about that. Just kind of know that. But there are a couple of things we do want to concentrate on. For instance, the Cambrian explosion, which we learned about, right? That's where we went from single-celled simple life to a huge amount of different forms and body forms and variety of life in the ocean. That was over 500 million years ago. So that's a very critical era as far as life on Earth is concerned. And we are currently, where are we now? We're currently in what's called the Anthropocene. And that notes the present time interval, and many geologic significant conditions and processes are heavily altered by human activity. So we are having a huge effect on the environment, of course, with global warming and the acidification of the oceans. We're in the middle of a mass extinction and caused by us. So who knows what's going to happen at this point? When things are not looking good for us. The Earth is going to be just fine over a long period of time. It will recover and things will change and be different. But human society is very delicate. We're not going to be okay from human warming of the Earth. Okay, so let's go back in time to the Hadean era where the dawn of life happened. So what was Earth like way back when? Terrestrial planets probably too small to accumulate atmospheres like the outer Jovian worlds, right? So when Earth's formed, it probably didn't have much of an atmosphere at all. Just didn't have the gravity to hold on to hydrogen or any other gas. Well, hydrogen mostly. I mean, most hydrogen is the most abundant gas around. And there wasn't much any other gas around. It's just, everything was mostly hydrogen. So that didn't work. Where did we get our atmosphere from? Well, as it turns out, volcanism. So volcanoes, kind of spurned on by geologic activity, belched out a lot of carbon dioxide and water vapor, and not much free oxygen at all. So all that carbon dioxide and water vapor was in the atmosphere and it remained a gas and kind of stuck around probably as gas. And it was way too hot on the Earth to have like liquid water. But eventually, as things cooled down, all that water vapor in the atmosphere started to condense and give us all the water on the surface that we know today. So that was like the mother of all rains, right? Can you imagine an entire atmosphere, an entire ocean up there condensing out and raining down on Earth? That would be an amazing sight. I don't know how long that really would have taken. If it was kind of a sudden thing, or that's a good thing. That's one thing I really want to look into. But anyway, that's where our water came from. It came from volcanism. The gas came from volcanism. So our atmosphere, what was left? It was mostly carbon dioxide. There was no oxygen in the atmosphere, no free oxygen. So what's going on here with the Earth? What's causing all this interesting activity that gives us our atmosphere and our water? What's going on under there? So we got the Earth, which is actually differentiated into different layers. Because it's big and was molten, the dense stuff sunk to the bottom, sunk to the center, I should say, and the lighter stuff kind of stayed out toward the outer areas here. That's called differentiation. Now, an object has to be kind of big enough for that to happen and also kind of molten for that to happen, right? The stuff has to be able to freely flow. But that's what happened, right? The iron and the nickel, the heavier stuff, the metals, all sunk down to the center of the Earth. And the mantle, which is made out of rock, much lighter material than metal, kind of stayed up here. So we have the inner core, we have the outer core, we have the mantle, and we have the crust. The crust is kind of like the outer edge, the lightest material. That includes igneous rocks. The crust is minimal in width, very small, scaled to the Earth. So an apple skin would be much, much thicker than the Earth's crust on the same scale if the apple was the Earth. Okay, so one thing we want to know about planets is this heat. So it's warm inside the Earth, right? It's almost energy. So what's happening is that there's all this energy left over from formation, some gravitational formation that's still kind of trapped in the Earth. So even after 4.5 billion years, the heat from formation, in addition to radioactive materials decaying, they're kind of maybe equally contributing to the heat inside the Earth. The Earth is radiating out all this heat. So as the heat is, making its way out here, it's hotter toward the center, right, than it is toward the outer part. It kind of makes sense, right? You put a potato in the microwave, you take it out, it's gonna be really hot at the center, but not so hot maybe further out, especially as it cools off. So what that does is that actually creates what's called convection. So in the rock, in the solid rock, it's actually causing it to move. So the rock is heated up here, and then as it gets hotter, it actually becomes less dense and floats up to the top here, where it's cooled off. And then as it cooled off, it sinks. And then it gets hot again, then it starts to rise, and so on, and creates these convection cells. Again, this is not like molten lava, or it's not lava, but it's magma or anything like that. The mantle is almost all solid rock. Solid rock can move over long periods of time like a lava lamp. I should have brought my lava lamp was right there. I should have brought it over. Anyway, so the solid rock is convecting. And that is a critical geologic process for life, because it's going to cycle the carbon and everything else, including giving us plate tectonics and resurfacing the Earth and depositing carbon and getting it out of our atmosphere. Okay, so one interesting thing about planets is that its size. So larger planets, after they're formed, are going to keep their heat, right? Longer than smaller planets. So again, you take a big potato and a small baked potato, you put them both in the microwave, right? Heat them up, or the oven. And then you take them out and you let them cool. Which one is going to cool off first? The small potato, right? The small potato is going to cool off a lot faster than the baked potato, right? There's just more stuff in the big potato to kind of keep that heat in. It's kind of intuitive. So this is another critical aspect of planets. The larger the planet, the more heat, internal heat, it's going to retain. And if it can retain internal heat, it can have these geologic processes like a magnetic field, which we'll talk about in a minute, but then also, convecting mantle to have a carbon cycle. Okay, and this is kind of what it is said on this next slide. Okay, plate tectonics. So Mercury and Mars are small. And so, like a small potato, they have apparently radiated all of their internal heat away. So that had dramatic implications for how the planet turned out. So that means that there's no plate tectonics, first of all. So there's no way to get the carbon out of the atmosphere. That means the mantle's not convecting. It kind of caused no plate tectonics. So it also means that there's no magnetic field. In other words, the convection at the core, which we'll talk about, is not happening. So the core is also convecting, the liquid part of the core. So the core could have partially solidified or at least stopped convecting. The metal, the liquid metal part of the core, that is a key component to having a magnetic field. So if it has no magnetic field, then the solar wind can come and grab on to the atmospheric molecules and over time strip all of the atmosphere away. So anyway, plate tectonics, motion of the plates is driven by the underlying convection of the mantle, which we talked about. Again, the mantle is a solid rock. And the initial strain from the mantle caused the lithosphere to fracture, leaving several pieces that kind of float on the mantle as it convects. So that's why these plates are sort of colliding and moving, because here convection is happening like in the middle of this mid-ocean ridge. Sorry, I'm using my cursor again. I've got to stop doing that. But between Africa and South America, between essentially Western Europe and North America, there's this mid-ocean ridge, right? It's called the Mid-Atlantic Ridge. And so that's where new material is coming up from the mantle, kind of upwelling on either side of this and pushing the plate this way, that's colliding and subducting under another plate over here. So that's why we have earthquakes and stuff like that over here on the San Andreas Fault and all the faults that happen along this line on the west coast in Alaska, and on the east coast of Russia, Japan, and all the way down to Indonesia and so on. Okay, so this is the mantle idea that I was talking about. The mantle, again, solid rock. In some, it's kind of like plastic-like in some areas with temperature and pressure, but it's not like molten lava. So get that idea in your mind. It's not molten lava, but it's like rock or almost, it is essentially rock. So it heats up. Over long periods of time, it moves. It creates this mid-ocean ridge of new material, and it's pushing. Then that material will kind of move over here, and then go underneath this and subduct here in a trench, and then that will heat up here. That can cause a lot of volcanism here. You get a lot of volcanoes around here and earthquakes, as you might imagine. This is the inner core. This is solid. This is the outer core, which is liquid. Metal, iron, and nickel and iron. Okay, the Earth's magnetic field is thought to be a result of a geodynamo. You need three things, we think. It's complicated. This is really a subject of intense study. Three things for a magnetic dynamo. So the first thing is that the interior region has to be electrically conducting. So no problem for a lot of planets. That's usually iron, right? Liquid iron. That's an electrically conducting fluid. You have to have convection in that fluid. In other words, the fluid has to be rising because it's hotter at the bottom. It's rising, cooling off, and then it's sinking again and getting heated and repeats the cycle. So it's creating this kind of convective motion. And then also, we think we need a moderate global rotation rate for a magnetic dynamo to take effect. So what that means is that you need all three of these things to create a magnetic field for a planet. So there's interesting exceptions to this. So you can look at the whole solar system and see who has a magnetic field and who doesn't have a magnetic field, and see if which rules they violate. So Venus, it's almost the same size as Earth, right? Why doesn't it have a magnetic field? That's kind of odd. Same composition, right? It's the same amount of stuff. There's no reason for it to be different. We know it's pretty much the same. But it's rotating very slowly. So it takes 243 days to make one day around the planet, right? For it to rotate once. So that's maybe too slow to generate a magnetic field. Although even that is under dispute. It's possible that that might even be enough to generate a magnetic field, in which case the reason it doesn't have one is kind of a mystery. So Venus has lots of mysteries, and that's kind of one of them. So radiation from the sun is not blocked by the Earth's magnetic field. So what does the magnetic field block? It blocks charged particles. So coming out of the sun, two different things. You have charged particles, like electrons and protons, and then you have light, electromagnetic radiation. Ultraviolet light, the light you see, X-rays, ultraviolet rays, all that stuff you're used to seeing. So the light is not affected by the magnetic field. It's going to go right through. So ultraviolet light can still, damage us. It's our atmosphere that protects us from ultraviolet light, as far as like life on Earth is concerned. But the charged particles can get diverted from the magnetic field and funneled either away from the Earth or funneled toward the poles. Because they follow them, they actually spiral down magnetic field lines. So kind of know that difference. The magnetic field protects us from charged particles, not from light. That goes for all the planets. Okay, and I kind of mentioned this before. Without the magnetic field, the solar wind would blow away all of the atmosphere through solar wind stripping. So a magnetic field is very important for protecting the habitability of a planet. So again, this is where sort of this all comes into play, right? If you have a planet that's too small, that loses all its heat after formation, it cools off, it's not going to have a convecting core, right? It's not going to have a magnetic field to protect the solar wind from stripping off its atmosphere, and then all of a sudden the planet does not have an atmosphere, or much of one, to sustain life. So planetary size has a huge impact on how life develops. At least life on the surface. Life under the surface is a totally different matter. But yeah, small planets, really hard to be habitable on the surface because of that reason. So it's kind of like a cascading effect. Also, small planet cools off fast. Yeah, if it had plate tectonics, plate tectonics slow down or they stop because the mantle isn't convecting anymore, right? You have no plate tectonics. You don't have the carbon cycle, which we'll talk about in a minute, to take the carbon out of the atmosphere. So maybe you do have a magnetic field for some reason, but then you have no plate tectonics, and you just have an atmosphere of carbon dioxide, so no oxygen. So that has a huge effect on how life develops. Okay, so what is the greenhouse effect? Well, it's just like a greenhouse. I'm sure you guys probably haven't thought a lot about how a greenhouse works. But basically, visible light comes into a greenhouse. I mean, I just bought a house. The house I'm in now actually has an enormous greenhouse attached to it. So I get to see this in action, like even today. Anyway, the sun comes in through the greenhouse and then hits objects, like hits the ground. And the ground warms up. That warming up means there's infrared radiation coming off of it, right? It's transformed the light from visible light, or whatever kind of light that's like ultraviolet light even, comes through the glass, hits the ground, warms up. Infrared radiation comes out. But the glass reflects the infrared radiation. It keeps it down. It keeps it from escaping. And that's how it heats up. Incoming radiation keeps heating up the greenhouse, but the greenhouse glass does not let that infrared radiation escape. So how does that work with the Earth's atmosphere? The same way. The light comes through the atmosphere. Again, that's not directly heating the atmosphere, except for the ozone layer. So there is an ozone layer. It does protect us from ultraviolet light, and it does heat up from that light, but it's not the global warming we're talking about. So kind of keep that as an aside. That heats the stratosphere. But we're talking about really near the Earth. So visible light comes in, it's totally transparent, also ultraviolet light and everything else, heats the ground. The ground warms up. Infrared radiation comes out. But then there's gases in the atmosphere that love to eat infrared light. They love to absorb infrared light. It's just like their thing. So once infrared light hits it, it absorbs it. And once it absorbs it, that heats up the gas. But then it re-emits another infrared wavelength photon, which is then absorbed by another gas, maybe the same gas. That heats that up. And then so on and so on and so on. The energy gets trapped as it's absorbed by the atmospheric gases after it warms the ground. So that's a critical thing. It warms the ground first, then the atmosphere absorbs the infrared radiation. Alrighty, so that's called the greenhouse effect. Which gases are we talking about that absorb the infrared radiation? It's carbon dioxide, methane, and water vapor. Those are the two big ones. Water vapor is a very potent greenhouse gas, so you have to kind of be careful about how much water vapor there is in the air, because that could really affect it. But carbon dioxide is a big one too, so is methane. But the problem is we are putting a lot of carbon dioxide into the atmosphere over the last 100 years, and is having a tremendous and undeniable effect on temperature, the global temperature, and this really going to really cause havoc with our lifestyle. Now, if we were not so dependent on technology and climate, and we weren't so connected to each other in many ways, it wouldn't be such a big deal. Maybe if we were in prehistoric times and we didn't build like all these giant cities on the edges of the coast, so when the poles melt, the Arctic is melting, and that causes a huge increase in sea level, and it floods Florida and puts all Florida underwater, we wouldn't be so affected. But we didn't. We actually did build giant cities on the coasts of our continents, and that can cause a calamity as all that stuff happens. Cause agriculture failures. We're all connected to the rest of the world. We're talking about a global, massive global change, and it's not going to be good for human civilization. Earth is going to be fine. It will recover over hundreds of thousands of years. But it's going to take hundreds of thousands of years, as you're learning. Okay, so Earth and Venus have similar amounts of carbon dioxide in the atmosphere. Earth stores the majority of its carbon dioxide in the carbonate rocks. Most of it is in the rocks. It's not in the oceans. Some of it's stored in the oceans, like a tiny amount. But the oceans are really important for getting the carbon from the atmosphere into the rocks. So where is most of Earth's carbon? It's in the rocks, 170,000 times atmospheric value. Some of it, a little bit of it, tiny bit of it, is in the oceans, 60 times atmospheric value. But it gets deposited in the oceans before it gets deposited in the rocks. So CO2 cycle does this, right? It goes from the atmosphere to the oceans, into the rocks, through volcanoes, back into the atmosphere. It goes, it starts condensing out as acid rain goes into the ocean. It settles down and is absorbed by the carbonate rocks on the ocean floors. And then that gets subducted by plate tectonics and transformed back into gas again. So that is the carbon cycle. It takes 400,000 years for the cycle to restore temperature due to carbon dioxide imbalances between the ocean and the atmosphere. And it is a negative feedback loop that's regulating Earth climate. What does that mean? Well, let's zoom in on this cycle a little bit. Yep. Okay, so on the right-hand side, what happens when things are too warm? So if things are too warm in the atmosphere, what happens? Well, that means there's more rain, right? There's more energy. There's been more evaporation, so there's more water up in the atmosphere. So there's more rain. So that means that more carbon dioxide can be dissolved in the rain and go into the ocean. And once it's in the ocean, it can get into the carbonate rocks and deposited there. So that means because of all that extra precipitation, that means not only does the carbon dioxide in the atmosphere kind of go down, but then that the temperature also will start to cool down as well. So weakened greenhouse effect will cool the Earth down because now there's less carbon dioxide in the atmosphere because of the more rain. Does that make sense? Okay, so on the left-hand side, what happens when it's too cool? If it's too cool, then there's less precipitation, right? And there's less CO2 dissolved in the rainwater to go to really get rained out. It builds up in the atmosphere. And of course, as we know, as we're living through right now, we have more carbon dioxide in the atmosphere. That's going to warm things up. That's going to push this temperature meter on the left up. So that's how the negative feedback works. And so you should definitely know how that works. Not just for this class, but you will be living through this for your entire life, unfortunately. So yeah, now you know what we're talking about, what we're up against. We're up against planetary forces of which we have no hope of counteracting, at least with our current technology. The only thing we can do is stop putting carbon dioxide into the atmosphere and then ride it out. Hopefully we haven't raised it enough, or else we have to wait hundreds of thousands of years. Okay, so geology plays a really critical role, right? Plate tectonics, volcanism, magnetic field, as we learned. We can use radiometric dating to carefully measure a rock's age. We have different ages, eons, Hadean, Archean, Proterozoic, and Paleozoic, with the one last divided into 3 eras of shorter periods. Don't worry too much about that. You probably know what the Hadean era is, I should say, maybe, but we're not going to get too much into the weeds in that. And then Earth's interior is divided into the core, mantle, and crust, while the lithosphere refers to the crust and part of the mantle. So kind of keep that in mind too. I may have skipped over that a little bit. Lithosphere is the crust and the upper part of the mantle. The internal heat of the Earth makes the mantle undergo convection. That causes plate tectonics. That causes subduction zones, and is a key part of having a carbon dioxide cycle. So Earth's core creates a geodynamo, responsible for the magnetosphere. Of course, that prevents the solar wind from stripping atmosphere, the charged particles from stripping our atmosphere. It does not prevent like ultraviolet light or light from coming in, but it does protect us from the solar wind of charged particles. Greenhouse gases, carbon dioxide, methane, and water vapor absorb the infrared light emitted from the planet's surface. It does not absorb the light coming from the sun. This is not sensitive to that. It absorbs the warm Earth, the light coming from the warm Earth. The absorbed photons act like a blanket, warming the planet's surface. We talked about the greenhouse effect and the CO2 cycle. And also, recent ice ages, I didn't mention this, but recent ice ages are tied to small changes in Earth's rotation and orbital. It certainly was in your homework, right? The Milankovitch cycles. We had recent ice ages where things got really cold and iced over, and even huge parts of the Earth became engulfed in ice. So why did that happen? Well, small changes in the eccentricity of the Earth's orbit and its inclination can cause this. because the Earth is not in this nice stable orbit constantly. Its orbit does change over time within a certain range. So it can be a little more oval at some points, and it's more circular, or it can be inclined. Its orbit can do this, and that can have an effect on climate. And then we had snowball Earths, which are the extreme kind of ice ages or large variations of temperature that ended more than 500 million years ago. We recovered from that from the carbon cycle. Alrighty, any questions? I think we just hit exactly 2 hours, like to the second. Amazing. I was hoping to do it in an hour and a half, but there is a lot of cover in this first exam. Alrighty, if there's no questions, I'll give you guys another minute or so. Thanks for coming. I will be in contact with you, of course, as the week begins next week. Don't forget, on Friday you have your quiz due and your participation response due. If you're watching this after Friday, hopefully you've done that already. And then the exam goes live on Monday. Alrighty, thanks a bunch. Bye.